A chemical change is a permanent, irreversible shift in composition. When a metal dissolves in acid, the resulting gas and liquid are entirely new substances with properties distinct from the original reactants. This differs from a physical change, such as melting ice. While the water changes state, the molecular structure remains H2O, and the process is reversed by simply lowering the temperature. At the molecular level, this transition consists of breaking the existing bonds within the reactants and forming new bonds to create the products. Understanding these transformations requires identifying the specific energy triggers that initiate bond breaking and the four models that govern how those atoms subsequently reorganize. Chemical bonds are stable structures. Because of this stability, atoms do not spontaneously rearrange. They require an external input to overcome their specific energy barrier. The process of breaking existing bonds always requires the absorption of energy from the environment. Conversely, when atoms form new bonds, the process results in a release of energy. The difference between the energy absorbed and the energy released dictates the requirements and the thermal profile of the reaction. Because bond strengths vary, different reactions require specific environmental triggers to initiate the transformation. Heat is a common trigger, breaking solid copper carbonate into copper oxide and carbon dioxide. Light energy also drives changes, splitting silver nitrate into silver, nitrogen dioxide, and oxygen. Finally, an electric current splits molten sodium chloride into metallic sodium and chlorine gas. A catalyst, such as manganese dioxide in the decomposition of hydrogen peroxide, can accelerate this process. The catalyst lowers the required energy input without being consumed by the reaction itself. While these triggers vary from light to electricity, the resulting atomic rearrangements follow predictable patterns. Reactions fall into four primary archetypes. First is direct combination, where two simple substances merge. For instance, burning carbon in oxygen synthesizes a carbon dioxide molecule. The second archetype is decomposition, where a complex substance breaks into simpler constituent parts. Thermal decomposition is irreversible. Heating calcium carbonate yields calcium oxide and carbon dioxide, which won't spontaneously revert. Conversely, thermal dissociation is reversible. Heating ammonium chloride separates it, but parts recombine when cooled. Combination and decomposition represent two foundational directions of chemical change, deassembly and disassembly of matter. The third archetype is single displacement. Here, a more active element forces a less active element out of its compound. This hierarchy determines which metals possess the required reactivity. Because zinc is higher on the reactivity series than copper, it displaces copper from a copper sulfate solution, forming zinc sulfate and isolating metallic copper. The fourth archetype is double displacement, characterized by the mutual exchange of ionic radicals between two compounds to form two new substances. This often results in precipitation, where the exchange creates an insoluble solid. Mixing silver nitrate and sodium chloride yields sodium nitrate and a solid precipitate of silver chloride. Another variation is neutralization. When an acid and a base react, they exchange radicals to produce only a salt and water. Unlike simple building or breaking, these displacement archetypes focus on the redistribution of molecular partnerships according to established chemical hierarchies. Since microscopic atomic interactions are not visible, we rely on macroscopic indicators to verify that a chemical change has occurred. One indicator is effervescence, the evolution of a gas. For example, reacting zinc and sulfuric acid produces visible bubbles as hydrogen gas is released. The sudden appearance of a precipitate provides further evidence. Clear solutions react to produce an insoluble solid that settles at the bottom of the container. Permanent color changes are also significant. Adding iron to a blue copper sulfate solution results in a light green ferrous sulfate solution. We also monitor thermal changes. Exothermic reactions release heat to the surroundings, while endothermic reactions absorb heat, causing the temperature of the vessel to drop. Macroscopic shifts in color, temperature, and state are the observable results of shifts in bond energy. To apply these principles, consider the reaction of solid iron in a blue copper sulfate solution. The reactivity series confirms iron is more active than copper, marking a single displacement. Iron breaks the copper sulfate bond. Copper is freed as sulfate bonds with iron. This shift creates a light green solution and a brown copper deposit, releasing energy in an exothermic process. This single observation demonstrates how bond energy, reactivity hierarchies, and macroscopic indicators function together. Chemical changes are deterministic, mechanical processes governed by the energy requirements of atomic bonds. Whether matter is combining, decomposing, or displacing, these four archetypes provide the framework needed to predict how substances will interact. Mastering these mechanics, the specific conditions where bonds break and form, allows us to predict and control reactions ranging from large-scale industrial synthesis to biological respiration.